The inspiration for our design came from research on the most efficient gliders in nature. The Albatros has a measured glide ratio of 20. This efficiency is primarily due to its large wingspan and rigid aerodynamic wing.
The first sketch shows what the glider should look like based on sources of inspiration. Further design considerations include a tapered wing for ease of modeling, long tail distance to improve stability, tricycle gear to make full use of ramp, and design for crash resistance and repair. The second sketch now evolves to account for the design considerations. Ramp equations are solved to find end ramp velocities. For each angle, different motors are used, and the one that provides the maximum velocity is selected. Friction between the wheels and the ramp was neglected. Glide equations are then solved for the trajectory. Each angle along with its maximum velocity is used as the initial condition, and the angle for furthest glide is identified. Assumptions include decoupling of lateral states, constant small angle of attack, and longitudinal static stability. The motor chosen was the Micromotor 5:1 HP. This yielded larger ramp end speeds than every other motor, as shown in the graph on the bottom right. The initial torque applied by the motor is 4 times too large to avoid skidding. The applied voltage has to be limited, hence the maximum velocity at the end of the ramp will be reduced. Once the wheels are spinning, the voltage will be increased to accelerate along the ramp. This can be visualized in the graph on the top right.
The horizontal distance covered can be maximized by varying the chord length. A range of chord lengths between 4 and 12 centimeters were analyzed, and the results are shown in the graph on the right. The optimum chord of 12 centimeters was chosen, which corresponds to the optimum ramp angle of 6 degrees, end of ramp velocity of 3.2 meters per second, and distance covered of 2.6 meters. Evolution of velocity, pitch angle, and the final trajectory obtained from the equations of motion are shown on the graph on the left. The model predicts the eventual stabilization about the equilibrium position. Our calculations for the initial design showed that the CG was too far aft of the aerodynamic center, and that in order to achieve stability, the motor needed to be moved forward. After switching to a front wheel-driven design, the CG was found to be at 6 centimeters from the leading edge, as shown on the figure. Our models identified certain key parameters that have to be met by our design, such as wingspan, total wing area, CG location, and distance of the tailplane to the CG. The design furthermore has to accommodate all the components for the drivetrain and the microcontroller. This preliminary design will now be manufactured and tested and subsequently improved.